Normandy, July 1944. The air over the bocage was thick with the smell of crushed vegetation and burnt cordite. According to the rigid mechanical logic of the German military, that tank was permanently erased from the immediate campaign. They scavenged intact tracks from a burned-out hull to fix a mobility kill. They dropped fresh radial engines into empty bays. They patched armor penetrations with raw steel plating salvaged from wrecked vehicles. The German intelligence ledgers simply could not account for an enemy that rebuilt its armored formations while the front line slept. By dawn, 3 of those 5 disabled tanks were idling at the edge of the camp, reloaded with ammunition and rolling back toward the exact same German positions. This mobile factory was the beating heart of American armored endurance. It transformed permanent battlefield casualties into temporary logistical delays. But an industrial assembly line is useless without a steady supply of raw material. The mechanics in the rear could swap a heavy transmission in hours, but they could not walk into a contested minefield to retrieve it. A disabled Sherman was a massive dead weight, often bogged down in thick mud, surrounded by hostile infantry, and perfectly zeroed by enemy anti-tank guns. To keep the maintenance companies fed, the army had to find a way to drag dead steel out of the kill zone. When the sun set over a contested sector, the battlefield rarely went truly silent. Flares drifted through the low clouds, and intermittent machine gun fire snapped across the darkness. For the German gunners, this was the time to rest, reload, and verify the locations of the smoldering American wrecks they had killed that afternoon. A shattered drive sprocket and a cracked transmission casing were not battlefield inconveniences. They were terminal wounds. They knew those steel carcasses were going nowhere. A 30-ton machine, stripped of its mobility, sinking into the soft earth, was a permanent monument to their marksmanship. But when the morning fog lifted, the German optics often found nothing but a vast, empty depression in the mud, flanked by deep, freshly churned track marks, leading back toward the American lines. The dead armor had been stolen in the dark. Bridging the lethal gap between the kill zone and the forward maintenance tents was the job of a highly specialized machine, the M32 Armored Recovery Vehicle. At first glance through a sniper's scope, the M32 looked like a standard Sherman. It shared the same chassis, the same engine, and the same thick lower armor plating. But instead of a heavy 75mm gun, it carried an immense steel A-frame crane, a massive towing pintle, and an internal 60,000-pound mechanical winch. It was a combat armored tow truck, crewed by men whose sole tactical objective was to drive directly into the line of fire and drag disabled assets back from the brink of total loss. The doctrine of armored retrieval was incredibly dangerous. The German military understood the value of a disabled tank and often kept their anti-tank guns trained on crippled Shermans, waiting to ambush anyone foolish enough to attempt a rescue. To counter this, American recovery crews operated under the cover of artillery barrages. In the German system, damage of that magnitude required heavy cranes, sterile engineering environments, and specialized transport. A crippled tank would be dragged to a rear railhead, thick mortar smoke, or total darkness. A typical operation required the M32 driver to reverse blindly into the impact zone, while a crewman crawled through the mud to physically attach heavy steel chains to the towing hooks of the dead vehicle. The physical constraints of this task were staggering. A standard Sherman weighed over 60,000 pounds. If its tracks were shattered or its internal transmission locked, it became dead weight. If it was buried to its lower hull in French mud, the sheer suction of the earth effectively doubled the required pulling force. The M32 would drop its heavy spades into the dirt to anchor itself, engaging the massive winch. The engine would scream under the load, the thick steel cables pulling so taut they could slice a man in half if they snapped. Inch by inch, the recovery crew would drag the paralyzed hull out of the crater, eventually towing it miles behind the lines to the waiting arc welding rigs of the ordnance companies. This aggressive recovery doctrine was the missing link that completely undermined the German intelligence officers, because the M32 teams successfully cleared the battlefields overnight. German units could not verify their actual impact on the American operational strength. The physical evidence of their victories simply vanished into the dark, denying them both the satisfaction of a confirmed kill and the opportunity to salvage the wreck for themselves. The system was undeniable on a localized, tactical level, loaded onto a heavy flat car and sent back to a major depot or even to the original factory in Germany. The process took weeks. A knocked-out Sherman was successfully retrieved by an M32, dragged to a mobile factory fitted with standardized parts, and returned to combat. But saving a handful of tanks in a small, isolated skirmish was one thing. The question was whether this intricate loop of continuous recovery and repair could survive the immense strain of an entire theater of war, where the casualty rates were about to spike to terrifying levels. The theoretical loop of recovery and repair faced its ultimate trial in the brutal geometry of the Normandy bocage. Here, the fighting was intimate, chaotic, and heavily favored the defender. Hidden PaK-40 anti-tank guns and infantry-wielding shaped charge Panzerfausts ambushed American armor at ranges so close they could not possibly miss. Within the first few weeks of the campaign, in the summer of 1944, some American tank battalions suffered casualty rates exceeding 50%. The narrow, sunken lanes were choked with burning, immobilized metal. If the localized repair system fractured under this pressure, the entire mechanized offensive would grind to a halt. The friction of this attrition was staggering. A single ordnance company, originally designed to handle steady, predictable maintenance, suddenly found itself buried under a tidal wave of shattered steel. Mechanics worked 24-hour rotations, fueled by cold coffee and adrenaline. The German crew had done this before. They knew what should happen next. A dead tank was supposed to stay dead, their arc welders throwing violent blue light across the mud. The demand for replacement components skyrocketed, threatening to drain the supply lines, stretching back to the crowded beaches of the English Channel. The system was bending under the sheer mathematical weight of the daily casualties as heavy steel booms lowered endless ruined engines into the dirt. But instead of collapsing, the logistical loop simply expanded. When the supply of factory-fresh transmissions or suspension bogies ran dangerously low, the mechanics turned the battlefield itself into an active warehouse. A Sherman that had burned completely to the ground, a total, catastrophic write-off, was not abandoned. M32 crews dragged these hollow, blackened shells into massive salvage yards. There, specialized teams aggressively stripped them down to the final bolt. They harvested intact track links, undamaged 75mm gun tubes, and viable internal components, sorting them into meticulously organized piles. The American military effectively constructed localized open-air factories built entirely from the wreckage of their own losses. The operational result was a level of resilience that defied every German expectation. An American armored division could lose 30 tanks in a vicious 3-day engagement. According to traditional doctrine, that unit was functionally gutted, incapable of further offensive action until fresh reserves shipped from across the Atlantic. This time, it did not. As the gunner scanned the leading edge of the new American assault, his crosshairs settled on a familiar olive-drab hull. Yet, within a week, the recovery crews and ordnance mechanics would cycle repaired, scarred vehicles directly back to the surviving crews. By Friday, the division would roll back out with 25 operational tanks. They absorbed devastating tactical defeats at the sharp end, while maintaining relentless strategic momentum behind the lines. The German forces were not blind to this cycle. They watched this continuous resurrection occur across the Western Front. German troops captured intact M32 recovery vehicles, examined abandoned American repair depots, and translated captured field manuals. They understood the basic premise: tow a damaged tank to a protected area, cut away the ruined section, and swap out the broken machinery. The concept was entirely visible and not a guarded state secret. Yet, even with this clear blueprint and a desperate need to preserve their own armored forces, the German military completely failed to replicate it. The obstacle was not a lack of effort, nor a lack of mechanical skill. To understand why the Wehrmacht could not simply copy the American method, we have to look at the fundamentally different way they chose to build a weapon. Deep inside a requisitioned French barn, a German maintenance crew wrestled with the heavy final drive of a Panther tank. The tank rolled forward, crushing the dirt beneath its tracks. But the front of the vehicle carried a massive, fresh scar. The massive steel component swung gently on the chains of a makeshift gantry crane. The mechanics carefully lowered it toward the exposed front hull, aligning the heavy gears. But as the metal met metal, the process abruptly halted. The heavy mounting bolts refused to align. The factory back in Kassel had slightly altered the bracket dimensions a month earlier to improve durability, but this specific Panther chassis was welded 2 months prior. The factory-fresh replacement part was completely useless unless the mechanics spent hours manually grinding and re-drilling the hardened steel. This was the bespoke trap of German armored design, where the American industrial base prioritized absolute, unyielding interchangeability. The German armament sector pursued continuous, isolated perfection. If a German engineer discovered a way to improve a suspension arm, upgrade a transmission seal, or thicken a glacis plate, that modification was implemented immediately on the assembly line. They rarely froze a design to prioritize mass production. As a result, German tanks evolved constantly. 2 heavy Tigers rolling out of the same factory doors just weeks apart could possess entirely different internal geometries, wiring harnesses, and track linkages. This pursuit of mechanical superiority created an absolute nightmare for the men swinging the wrenches in the field. A captured American manual detailing rapid field repair was worthless if the spare parts arriving on the supply trucks did not physically mate with the broken vehicle. A thick, bright line of raw welding crawled across a replacement transmission cover. The right track was entirely new. A German mechanic could not confidently scavenge a cracked transmission from a dead Panther and bolt it into another Panther, because the gear ratios, the casing dimensions, or the linkage connections might have subtly shifted between production batches. Instead of a rapid, modular swap, every major repair turned into a custom refit, demanding master craftsmen rather than assembly line mechanics. The barrier to rapid repair was also baked directly into the physical architecture of the vehicles. The heavy German armor, specifically the fearsome Tiger and Panther lines, utilized a complex, interlocking road wheel suspension system. This engineering choice provided a brilliantly smooth ride, distributed the immense weight of the armor perfectly across the mud, and provided extra protection for the lower hull. But if a single inner wheel was shattered by an anti-tank mine or a high-explosive shell, the mechanics could not simply pull it free. To replace one broken inner wheel, the crew had to unbolt and extract up to 5 heavy outer road wheels just to reach the damage. A track repair that took an American ordnance crew 45 minutes could easily consume half a day of exhausting labor for a German squad. German tank engineering was fundamentally incompatible with the American model of rapid, standardized recovery. The German military built exceptional, highly lethal, and heavily armored hunting machines, hanging with a slightly different tension than the left. It was the exact same machine they had killed 3 days earlier, but they built them as individual, hand-fitted masterpieces rather than interchangeable, modular tools. When a heavy German tank broke down or absorbed battle damage, it inherently required a stable environment, heavy lifting gantries, precise tools, and time to carefully coax the bespoke machinery back to life. But in the late summer of 1944, stable environments were rapidly vanishing from the map. The critical problem was no longer just the complicated machinery itself. The deeper issue was what happened when this rigid, delicate maintenance network was suddenly forced to operate under the absolute collapse of its own strategic supply lines. The rail yard at a French transport hub, autumn 1944. A heavy flat car sits paralyzed on twisted steel tracks. Strapped to the timber decking is a damaged Panther tank with a cracked transmission housing. Under the old rules of German doctrine, this train would arrive at a well-lit rear depot within days, where gantry cranes would gently extract the broken machinery. But the sky is now dominated by the heavy drone of Allied fighter bombers. A P-47 Thunderbolt had shattered the locomotive's boiler hours ago. The Panther is stranded miles from any factory, perfectly recoverable in theory, yet totally dead in reality. German doctrine fundamentally relied on a massive, uninterrupted railway network to sustain its bespoke maintenance system. Because their mechanics could not execute heavy, modular repairs in a mud-soaked field, the entire life cycle of their armor was tethered to the rails. When a Tiger or Panther suffered a severe mobility kill, this was not an isolated illusion. Across the Western Front, from the hedgerows of France to the dense forests of the Ardennes, it was dragged out of the fire by a specialized recovery vehicle, such as the Berger Panther, and towed straight to a train station. Crucially, these German recovery vehicles were not designed to drag 50 tons of dead steel across hundreds of kilometers of open countryside. They were strictly short-range shuttles. By the summer of 1944, the Allies owned the skies over Western Europe. Fleets of fighter bombers systematically dismantled the French and German rail networks. They bombed the marshalling yards, dropped bridges into rivers, and hunted heavy locomotives through the valleys. The strategic logistical tether was violently and permanently cut. When the railheads vanished, the physical distance between a damaged German tank and its necessary repair depot expanded from a short shuttle run to an impossible overland journey. If a heavy German tank snapped a drive sprocket or overheated an engine during a fighting retreat, the crew could no longer load it onto a flat car. If they attempted to tow the massive dead weight using another combat tank, the immense strain would inevitably shatter the towing vehicle's delicate internal gears, immediately turning one casualty into two. This logistical collapse forced a bitter, terminal reality upon the German tank crews. They were suddenly ordered to perform a task entirely opposite to the American recovery doctrine. Instead of pulling salvageable armor away from the front line, German crews were forced to execute their own machines. Men who had survived fierce armored engagements had to dismount, unpin high-explosive demolition charges, and drop them. Inside a concealed anti-tank position, a German gunner wiped the sweat from his eyes and pressed his face against the rubber cup of his Zeiss optic. German anti-tank units, artillery observers, and tank commanders began reporting the same impossible phenomenon. They were scoring confirmed, verified hits down the breeches of their own long-barrel guns. A heavy German tank with a minor mechanical failure, a broken fuel pump, a shattered track pin, or a warped final drive was no longer a temporary tactical setback. Without the trains to carry the bespoke machinery backward, and without the standardized parts to fix it forward, a simple mobility kill became a permanent loss. The German combat ledgers filled rapidly, not just with tanks completely destroyed by American armor-piercing shells, but with perfectly salvageable engineering marvels detonated by their own crews on the muddy shoulders of retreating dirt roads. The inability to replicate the American repair method was not simply a matter of German troops ignoring a good idea. It was the fatal consequence of an inflexible industrial philosophy crashing into the brutal reality of an isolated battlefield. The enemy could clearly see the American system working, but their own military infrastructure was structurally incapable of matching it. As the campaign reached its final stages, this collapse revealed the ultimate lesson of the conflict. The war of attrition would not be decided by who built the finest individual weapon, but by a very different kind of calculation. When the German gunner in the Normandy bocage stared through his Zeiss optic at the scarred Sherman rolling back into the fight, he was not witnessing a failure of his own marksmanship. His 75mm shell had struck perfectly. They were watching American armor bleed oil, shed tracks, and grind to a complete halt. They were marking the kills in their ledgers. The kinetic impact had shattered the heavy steel, casting exactly as his manuals promised. The math of the kill was flawless. The mystery was never really about the thickness of American armor or the lethality of the German gun. It was about a fundamental collision of two entirely different philosophies of war. The German military had engineered a battlefield ecosystem built around the individual masterpiece. They poured their industrial capacity into creating the most lethal, highly specialized hunting machines on the continent, demanding bespoke perfection down to the final bolt. But that perfection was brittle. When the friction of a brutal campaign cracked that armor and the strategic rail lines collapsed under aerial bombardment, those isolated masterpieces were marooned. A crippled Panther, unable to reach its specialized factory, was no longer a weapon. It was a roadblock waiting for a demolition charge. The United States military chose a different path. They accepted that tanks would die. They planned for attrition, understanding that heavy armor would inevitably be shattered, burned, and immobilized by a highly competent enemy. Their response was not to build an indestructible fortress, but to build an interlocking, relentless system of mechanical recovery. That system was not an abstract theory. It was not simply a matter of having more factories back in Michigan. Yet, within days, and sometimes within hours, those identical vehicles were returning to the fighting line. It was a physical chain of heavy labor and immediate, localized adaptation. The American method relied entirely on the men who were pushed into the mud to make the modular design work. It relied on the crews of the M32 armored recovery vehicles, reversing blindly into the dark to wrestle 60,000-pound chassis out of contested craters, trusting their heavy steel winch cables to hold under fire. It required the draft-age mechanics in the forward ordnance companies who operated heavy lathes and air compressors under the constant threat of counter-battery barrages. These were the former rail yard machinists, automotive welders, and Detroit assembly line workers who treated ruined armor not as a lost cause, but as a temporary mechanical failure. They severed warped steel with oxyacetylene torches, drove out fused suspension pins with heavy sledgehammers, and dropped standardized, interchangeable transmissions into empty bays before the sun came up. They aggressively cannibalized the dead to keep the living moving forward. The German military could capture the field manuals and inspect the repaired hulls. But they could not copy the method because they lacked the industrial DNA that made it possible. The American strategy essentially dragged the factory floor directly to the front line, turning the scarred geography of Europe into an active warehouse of standardized parts. In the end, the ghost fleet that systematically dismantled the German defensive lines was not driven by impossible engineering. They rolled back into combat, bearing the crude, welded scars of their previous deaths, firing on the very same German positions. It was propelled by the grease, the blinding arc-welding sparks, and the exhausting manual labor of thousands of unnamed mechanics. When that previously dead Sherman crested the ridge, bearing a thick, bright line of raw welding across its nose, it was carrying the true weight of the conflict. It was not just a single vehicle surviving the battlefield. It was an entire industrial machine, bolted together in a muddy pasture, rolling inexorably forward. To the German soldiers looking through the optics, it felt as though they were fighting an enemy that could simply rewind the consequences of physics. They had captured American equipment and interrogated mechanics, but understanding that a machine could theoretically be fixed was entirely different from watching a shattered hull resurrect in the middle of a war zone. The math of the battlefield was changing right in front of them, breaking every rule of mechanical engineering they had been trained to trust. To understand why this ghost fleet was systematically dismantling the German defense, we first need to understand why the men pulling the triggers believed their kills were absolute. For a German anti-tank crew in 1944, a confirmed kill was not a guess. It was a mathematical certainty. 400 meters across the field, the heavy engines of an American armored advance vibrated through the earth, verified through some of the finest optical equipment in the world. When an armor-piercing round struck a target, the gunner watched the sequence unfold through highly magnified, strictly calibrated lenses. They saw the violent flash of the kinetic impact. They looked for secondary explosions, the sudden venting of internal pressure, or the abrupt, grinding halt of a 30-ton machine. If the enemy crew abandoned the smoking vehicle, the ledger was updated. The threat was mathematically neutralized. This confidence was not born out of arrogance. It was deeply rooted in the German military's own mechanical reality. In the Wehrmacht, armored warfare was a precise, highly engineered science. A tank like the heavy Panther or the ubiquitous Panzer IV was a formidable weapon, but it was also a delicate ecosystem of interlocking, highly specialized parts. If an enemy shell cracked a Panther's transmission, twisted its chassis, or warped its turret ring, the immediate tactical life of that vehicle was permanently over. German doctrine divided battle damage into strict categories based on the echelon of repair required. Minor issues, a thrown track, a fouled spark plug, a damaged road wheel could be handled by the crew or a forward mechanic. But structural trauma required a fundamental reset. The gunner had held this exact same angle 3 days earlier. He knew the distances. He knew the sightlines. A shattered transmission in a German tank often meant lifting the massive turret, unbolting the heavy superstructure, and carefully extracting the ruined machinery with heavy cranes. That level of industrial lifting simply could not happen. In a mud-soaked crater under mortar fire, the crippled machine had to be winched away, loaded onto a specialized flat car, and transported back to a regional repair hub or a factory deep within Germany. Because this was the unbreakable rule. For their own armor, German intelligence naturally applied the exact same rule to the enemy. When a Wehrmacht officer tallied the daily combat reports in a dimly lit command post, a disabled American tank was crossed off the operational roster. The German High Command relied on these numbers to ration their dwindling reserves and plan their defensive lines. If a localized counterattack immobilized 15 American tanks on a Tuesday, the German commander calculated that the American formation would be desperately under strength on Wednesday. It was simple, undeniable attrition. But as the campaign dragged on, the meticulously kept ledgers began to lie. German defensive positions were repeatedly assaulted by armored units they had supposedly annihilated just days prior. And he knew exactly what was supposed to be sitting dead in the mud on the far edge of the pasture. The German gunners were not fabricating their reports. They were accurately recording mobility kills, armor penetrations, and shattered drive sprockets. The failure was not in their eyesight, nor was it in the lethality of their anti-tank guns. The failure was a complete inability to comprehend that the American military defined a destroyed vehicle under an entirely different set of rules. To the German engineering mind, a machine with a cracked hull and a ruined transmission was dead metal, requiring a factory to resurrect. They assumed the Americans were operating under the same immutable laws of logistics. If a Sherman was gutted on a French road, it should take weeks to return, assuming it was not abandoned entirely. Yet, the identical Shermans kept rolling back over the horizon. The mathematical models of attrition were breaking down. What the German troops could not see through their optics was that the American tanks had not been designed as perfect, isolated fortresses. To understand why a crippled Sherman could survive a fatal blow, we must look away from the battlefield and look inside the physical architecture of the machine itself. The secret to the Sherman's resurrection did not begin in a European military academy. It began on the automotive assembly lines of Michigan and Ohio. 72 hours prior, this German crew had fired a 75mm armor-piercing shell directly into the leading American Sherman. The gunner remembered the specific, catastrophic impact. When the United States War Department finalized the design for the M4 medium tank, they handed the blueprints not just to traditional arsenals, but to locomotive companies and car manufacturers. These industries did not view the tank as a bespoke, handcrafted piece of mobile artillery. They viewed it as a heavy-duty tractor with a gun. That fundamental shift in philosophy birthed the single most important mechanical advantage of the war: absolute interchangeability. In the German manufacturing system, heavy armor was often hand-fitted by master craftsmen. A mechanic replacing a damaged final drive on a heavy German tank might discover that the replacement part required hours of filing, drilling, and machining just to align with the hull, simply because manufacturing tolerances drifted from one factory batch to the next. The American industrial system rejected this completely. A transmission assembled by Chrysler on a Tuesday had to slide seamlessly into a hull welded by Fisher Body on a Thursday. Every bolt hole, gear tooth, and mounting bracket was machined to exact, unvarying standards. This demand for standardization directly influenced the physical architecture of the Sherman. Consider the massive cast steel nose of the vehicle, the exact area shattered by the German shell in our opening scene. This rounded housing protected the transmission, the differential, and the steering brakes. In many contemporary tank designs, reaching these vital internal organs meant the high-velocity round had shattered the right drive sprocket and cracked open the massive cast steel transmission housing on the front of the hull, lifting the multi-ton turret with a heavy crane and hoisting the machinery out through the roof. The Sherman was engineered specifically for the mechanic in the dirt. Its entire front differential housing was bolted directly to the hull with a ring of heavy fasteners, rather than being welded permanently into the frame. To a field repair crew, those bolts changed the entire nature of a battlefield casualty. If an armor-piercing round gutted the forward gears, the tank did not need a train ride back to an industrial center. A maintenance crew could sever the damaged fasteners, detach the ruined 3-ton steel casting, and slide a fresh, pre-assembled transmission module directly onto the front of the vehicle. The broken unit would be sent to the rear for rebuilding, while the tank itself returned to the fight. It was a massive, lethal application of modular engineering. Because of this, the Sherman was less a fixed object and more a collection of compatible components. Radials, engines, track links, bogie suspensions, and gun mantlets could be scavenged, swapped, and bolted together from the wreckage of entirely different vehicles. If an American ordnance depot received 3 critically damaged Shermans, they could often cannibalize the surviving halves and assemble one fully functional tank within 48 hours. The German gunner on the ridge was not fighting an individual machine. He was fighting an interlocking automotive supply chain. The metallic shockwave had echoed clearly over the gunfire. White smoke had immediately poured from the lower chassis. But blueprints and identical spare parts are only theoretical advantages. Perfect interchangeability meant absolutely nothing if a crippled tank was left burning in the mud of a contested kill zone. The American tank was physically capable of rapid, localized repair, but steel castings do not install themselves under artillery fire. To turn Detroit's engineering into a relentless tactical weapon, the military had to bring the factory directly to the front line. The reality of American field maintenance was not a pristine factory floor. It was a rutted, rain-soaked pasture under a camouflage net, vibrating with the roar of portable gasoline generators. To keep the mechanized assembly line moving, the United States Army pushed its heavy industrial capacity dangerously close to the front lines. These were the ordnance maintenance companies. Unlike the German system, which inherently relied on pulling damaged armor backward to the safety of established rail networks, the American doctrine dragged the mechanics forward into the mud. They operated mere miles behind the fighting, often well within range of heavy enemy artillery. An American forward maintenance depot looked less like a standard military encampment and more like a mobile industrial yard. Heavy cargo trucks towed massive canvas tents and specialized machine shops. Mounted directly inside those vehicle beds were power lathes. The American crew had thrown open their hatches and sprinted into a nearby ditch. The vehicle was completely immobilized. It was a textbook mobility kill. Drill presses, heavy-duty air compressors, and industrial arc welding rigs. The personnel staffing these units were not simply riflemen handed a wrench. They were union machinists, auto workers, and master welders who had been drafted out of civilian rail yards and automotive plants. They intimately understood how to work with heavy steel under pressure, and the military provided them with the industrial infrastructure necessary to manipulate 30 tons of armor in an open field. The daily work was brutal, deafening, and relentless. When a Sherman arrived with a shattered front differential, like the one struck by the German gunner, the maintenance crew did not waste time, carefully disassembling the ruined geometry. They used oxyacetylene torches to violently cut away warped armor and fused metal. Sledgehammers drove out deformed suspension pins. 10-ton wrecker trucks backed into the deep mud, deploying heavy steel booms to hoist the dead weight of a ruined transmission out of the hull. Because the replacement parts were perfectly standardized, the mechanics only had to lower the new casting into place, torque the massive bolts, and weld the seams shut. The sheer volume of this localized effort continuously overwhelmed the German mathematical models. A German tank battalion commander might report a decisive defensive victory at sunset, accurately claiming 5 Shermans definitively disabled. But overnight, under the glare of shaded blackout lights and showering sparks, American maintenance companies worked in overlapping shifts.